Hello, my name is Yuanyuan, a second-year PhD student in Northeastern University showing behind. Today, I'm going to talk about my recent work, Universally Stable Cache Network, which is collaborated with my supervisor, Stratis Ioannidis. Before I introduce our universally stable cache networks, we first talk about what is a cache network. In a cache network, when a request is generated, it is routed to a server which permanently stores requested items. Each node is equipped with finite storage space, which could store requested items and serve item requests. Thus, upon hitting a cache which stores the requested item, a response carrying the item is backpropagated over the reverse path. We would like to study cache networks because cache networks are a nature abstraction for many applications, including information-centric networks, content distribution networks, P2P networks, and so on. In the work of Ioannidis and Ye, they consider a cache network where each edge is assigned a routing cost. They want to determine how to cache so that costs are minimized. This problem is NP-hard, but because it is a submodular maximization problem under matrix constraints, it can achieve a 1 minus 1 over E approximation ratio. Instead of routing cost, in Martin's work, they associated downwards edge with MM1 queues. They want to determine how to cache to minimize costs. These resulting costs capture queuing and not linear anymore. Their problem is still NP-hard. Since it is a submodular maximization problem under matrix constraints as well, they obtain a 1 minus over E ratio. In their work, they consider MM1 queues. In MM1 queue, all responses are served individually by the server. This is convenient from a modeling perspective because MM1 queues form a Kelly network, whose joint distribution in steady state has product form. However, transmitting responses individually leads to a problem. When many responses carrying the same item arrive simultaneously, all of them are queued. However, the additional responses are redundant. The response on the server can be transmitted once and serve the requests. This redundancy leads also to other problems, like MM1 queue can be potentially unstable when the load is larger than 1, even when the queue just contains responses with the same item. The goal of our work is to address this problem due to redundant responses. To do so, we introduce the notion of MM1C, or counting queue. In a counting queue, when a response arrives, it will be served immediately. If before service finished, a same-time response arrives, instead of queuing up, it merges with response in the server, and they are served simultaneously. We call it a counting queue because both queue and response are associated with a counter to record the number of response merged. No matter what the load is, the queue is always stable. This counting queue has the advantages of being stable precisely because the responses are merged. However, due to this merge behavior, the departure process is no longer following a Poisson process, and a network of counting queue is not a Kelly network. It is hard to describe its steady-state distribution in a closed form. We associate the downward edges with such counting queues, and responses are queued back upon a cache hit. We would like to determine how to place items in caches and assign service rate jointly to minimize steady-state queuing costs. To achieve this goal, we met 3 challenges. First, counting queues network is not a Kelly network. It is hard to describe it in a closed form. Second, this joint optimization is NP-hard. Besides, service rate is continuous while cache assignment is 0-1 problems. This mixed integer problem cannot rely on submodularity in the previous mentioned works. Corresponding to these challenges, we make the following contributions. First, we model network as a network of counting queues, which is more realistic and universally stable. Second, we prove that MM1C queue can be closely approximated by MM-infinity queues. Third, by utilizing DR submodularity of objective, we could jointly optimize item placement and service rate assignment with a 1-1/E approximation algorithm. My talk consists 3 parts. First is our model, then we obtain some main results from it. Finally, we use experiments to verify our results. Our network is represented as a directed graph. Each node has a cache with capacity CV. Items stored and requests constitute the item's catalog. Binary variable XVI indicates whether node V is caching item I. Because of the cache capacities, sum of X over item should be less than CV. Our global item placement is denoted by bold X. Items are permanently stored in some certain network nodes called designated servers. Due to these designated servers, requests are always satisfied. A request is determined by the item it requests and the path it goes through, which is from user to a designated server. These requests are generated according to a Poisson process, and the set of responses passing through edge E is denoted by demand RE. We assume requests are negligible, but response incur traffic in the network. We model this traffic as follows. Every edge is associated with service rate μE. The service rate in an edge E is split across response type μER. So the sum of μER over responses should be less than μE, and the global service assignment is denoted by bold mu. For a counting queue, the counter value is denoted by NER, and its corresponding cost is a non-decreasing function of it. Our optimization objective is to minimize total expected cost over all the edges and responses. To sum it up, our problem is to minimize total expected costs under certain item placement and service rate assignment constraints. We know that it is hard to formulate counting queues network in a closed form, but if we assume Poisson arrivals with counters equal to 1, we derive below steady-state distribution. In fact, it is only true in the edges directly adjacent to a designated server, because intermediate queues may have neither Poisson arrivals nor counter equal to 1. To form a Kelly network, we could approximate MM1C queue with MM-infinity queue. Recall that MM-infinity queue has infinity servers. Just as in a counter queue, incoming responses are not queued but are immediately served. Their steady-state distribution is like below. Although these two steady-state distributions are quite different, they are still closely related. First, observe that both queues are universally stable. Incoming responses won't queue and be served immediately. Second, they exhibit the same aggregate service rate. For example, when there are 3 responses in the queue, all the responses receive the same service rate in these 2 queues. Third, their moments are bounded by each other. We prove this in a theorem that for arbitrary loads, the 2 moments are bounded by k factorial, which is the order of the moments. In particular, when k equal to 1, the theorem implies that the expectation of 2 queues are exactly the same. Given the steady-state distribution, we'll formulate our approximate problem as following. Actually, they are all approximation of networks of counting queues. For MM1C queues problem, the objective assumes Poisson arrivals and counter is equal to 1 at intermediately queues. This assumption only holds for edges directly adjacent to a designated server in the real world. For MM-infinity queues problem, it is approximation as we use MM-infinity queues instead of MM1C queues. To solve these two approximate problems, we first assume that the cost function is convex. Then these two problems can be formulated in a more general form. Here, the objective is non-decreasing and convex with respect to load. If we can solve this problem, we can also solve both two approximate problems before. We first consider an equivalent cache gain maximization problem instead of cost minimization problem. Its objective is not concave and it is NP-hard. What's more, because it is a mixed integer problem, it is not submodular, so we cannot use the techniques in the previous work we mentioned. So we use multilinear extension to extend integer x to a continuous domain. We prove that this multilinear extension is their submodular joints on mu and y. By leveraging their submodularity, we adopt Frank-Wolf-Barrett algorithm to produce an approximate fractional solution y and mu. Finally, the fractional solution y is rounded into an integer solution x, and our overall algorithm provides a 1 minus 1 over e approximation guarantee in expectation. Finally, in our experiment part, we have both offline evaluation and the online evaluation. In the offline evaluation, we'll compute the expected costs. Let's look at this figure. The x-axis is 8 different topologies. We compare our algorithm's results with others, and we outperform them a lot. In the online evaluation, we simulate responses in a MM1C and MM-infinity queues network and compute the time average costs. Please note that, different from offline evaluation, we do not assume any Poisson arrivals with counter equal to 1 in these online simulations. We compare our algorithm with others who has dynamic item placement. Ours still outperforms them dramatically. In this experiment, we confirm the quality of our two approximations of counting queues. The x-axis in the figures is order k of the moment, which is the cost function in our evaluations. The left figure is the expected cost in the offline evaluation, where the right figure is the time average cost in the online evaluation. we notice that nearby columns are results produced by two solutions solved by our two approximate problems. Even though these two objects are not the same, the quality of the solution that they produce is quite similar. And here we find out the expected costs are almost identical to the time average costs. This is anticipated for infinity queues because it forms a Kelly network, but it is not obvious for M1C queues. In offline evaluation, we assume Poisson arrivals with counter equal to 1 to formulate the steady state behavior. But surprisingly, this still achieves similar results as in online evaluations. Finally, observe that objective values of infinity and M1CQ's network with the same solutions. They are bounded by the K factorial, which is verify the theorem we mentioned before. In conclusion, we model a cache network as a system of counting queues in which identical responses merge when collocated. We jointly optimize item placement and service rate assignment with a 1-1/E approximation algorithm. In this work, we propose an offline algorithm, and a fully adaptive algorithm would be interesting to study. And merging on the basis of item other than the request type in our work is an interesting practical directions. They are harder to analyze, but they could gain intuition from our setting. This is the end of my presentation. Thank you for your patience and listening.